Hello everybody, welcome to another video on Thomas's calculus. This time we are going to look at chapter 14, specifically Lagrange multipliers. That's 14.8. Let's look at an example. This question says, let's find the greatest and smallest values. That's the minimum and max, minimum. These are also known as critical points, as you know. Critical points of the function f(x), xy. And the constraint is an ellipse. This is a constraint. So this is the function and the constraint is x. This is the constraint. So what we are asked to do is find the critical points. We can call them x0, y0. So here we know that at the critical points, the gradient vector of the function is in the same direction as the gradient vector of the constraint. Because of that, Lagrange mentioned that the gradient vector of the function at the critical point x0, y0 can be written as f(x0, y0) equals lambda times the gradient of the constraint. Gradient of the constraint, which is called gx xy at x0, y0 at the critical point. Now here we take the constraint and take all the variables on one side and put the constants on the other sides, and we only consider the side where the variables are. So all the function with all the variables, the side of the function with all the variables are called gx here, because these constants don't really contribute to the gradient. So this can be written as you know, it's a vector, partial derivative of f with respect to x, partial derivative of x at x0, y0, partial derivative of f with respect to y at x0, y0, because this phenomena only holds at the critical points, is equal to lambda partial derivative of g with respect to x. This is a vector, so it's a point, we use pointy brackets there, at x0, y0, comma, partial derivative of f with respect to y at x0, y0. So for convenience, we write it this way. So we write it as partial derivative of f with respect to x at x0, y0. And then below we put partial f with respect to y at x0, y0 equals lambda and vector sign again, partial derivative of g with respect to x at x0, y0, and partial derivative of g with respect to y at x0, y0. So when you do this, it is easy to identify that these values can be grouped together because they are partial derivatives with respect to x, and these values can be grouped together, and we can make one equation with the greens where you can equate the partial derivative of x with lambda to this, and then we can equate partial derivative of y to this equation. So we can make two equations here, and the third equation would be, because we want to find x0, y0, and we have a lambda and x0, y0, the third equation would be the constraint with the constant, which would be x0 at the critical point, x0 squared, because the critical point has to be on the constraint, so it will be x0 plus y0 squared over 2 equals 1. So these are the three equations. So let's rewrite these equations. So we'll rewrite the equations, keeping space to solve the problem. So we have, we'll write the partial derivative of f with respect to x at x0, y0 as pink, and then we'll write partial derivative of f with respect to y at x0, y0 in green, because that's the y derivative would be equal to lambda times. Again, we'll write the partial derivative with respect to x. This time it is g, if you remember, x0, y0, and g with respect to y. Partial derivative of g with respect to y at x0, y0. So let's combine the equations and write the equations now. So let's look, now we have, this is fx, y is equal to xy, that's the equation. If we take the partial derivative of f with respect to x, we know we get y here. Partial derivative of f with respect to y, we get x. So we'll put these values back to this. Sorry, maybe I should not draw over this. So we'll put that to these brackets. So we have within the brackets, we say it is, will follow the same procedure. So this is partial f with respect to x would be y, and partial derivative of f with respect to y would be x, and that would be equal to, should change the color, should be equal to lambda times, now we'll go and get the g. So g of partial derivative of g, so we know g is equal to this part. So let's do the partial derivative of g with respect to x would be, this is gxy, would be 2x over 8, and partial derivative of g with respect to y would be 2y over 2. So let's, so we have to include this here, and we know that partial derivative of g with respect to x is 2x over 8. We can simplify that further, so we get x over 4, and then we will write the next one. We'll simplify it here, so it will be y. So now we have two equations. We can equate these two and get one equation. I should probably draw that in pink. So that will be in pink. This would give you one equation, and this would give you another equation in green. So let's look at the this equation would be y equals x lambda, x over 4. And if we look at the other equation with respect to y, it would be x equals lambda y. Now we also mentioned that this is only equal when it's at the critical point. So it is not, it is always good to remember that this is at the critical point. We can drop the x0, y0 and generalize it, and always remember that whatever solutions we get is for x0, y0. But I would like to mention that this is at the critical point. There's one more equation that's true at the critical point, is this equation. So it's also true that at the critical point, x0, y0 This equation is satisfied because the critical point x0, y0 has to be on the constraint. That is another condition. So we have 1, 2, and 3 equations. So let's copy these equations to the next slide and work through that. So for simplicity, we are going to remove the 0 from x0. So we'll delete them, we'll consider them as, if I can delete that, we'll consider them as x and y. But remember that this is only possible at the critical points. It holds only, Lagrange holds only at the critical point. For simplicity, we'll just remove that and let's do the calculation. So we see from 2 we see x is equal to lambda y. So we'll substitute x from here to this equation. So we see y equals lambda times x is equal to lambda y, and also there is a 4. So this lambda y was substituted to x. So we can cross off y here and we see lambda squared equals 4. So lambda is equal to plus or minus 2. And we also can say that when x is equal to 0, y is equal to 0. We know that, we see that when x is equal to 0, y is equal to 0. But in the ellipse, this x0, y0 is not a point on the ellipse, so we can cross that off. But we have lambda equals a plus or minus 2 here. So one thing we can do is we can divide the page into 2 and calculate when lambda equals minus 2, and on this side it will be when lambda equals 2. What happens when lambda is equal to 2? So when lambda is equal to 2, we know x is equal to 2y. That's from this equation. X is equal to 2y when lambda is equal to 2. And similarly, when lambda is equal to minus 2, x is equal to minus 2y when lambda is equal to 2. It's equal to minus 2y. So if x is equal to 2y, let's substitute it to 3. When you substitute to 3, you get 4y squared over 8 plus y squared over 2 equals 1. So, but if you simplify this further, you get half here. So we have half y squared, and half y squared is y squared equals 1. This implies y is equal to plus or minus 1. But it gets a little easier because when you substitute x equals minus 2y to this equation 3, you basically get the same thing because it's squared. So minus 2y squared over 8 plus y squared over 2 equals 1. Fortunately, that makes it much easier. We get it's y squared over 8 plus 4 over 8 y squared over 2 equals 1. So we still get y squared equals plus or minus 1. Y equals plus or minus 1. So now what we need to do is look at when y is equal to 1. Now I'm going to separate this out again. And when y is equal to 1 and y is equal to minus 1. When y is equal to 1, x is equal to, and lambda is equal to 2, x is equal to 2. When y is equal to minus 1, x is equal to minus 2. So also we can say when y is equal to, let's say when lambda is equal to minus 2, y is equal to 1, and when y is equal to minus 1. So when y is equal to 1 and lambda is equal to minus 2, we have, here we see that x is equal to minus 2. Sorry, it should be minus 2. Is equal to minus 2, and when lambda is equal to minus 2 and y is equal to minus 1, x is equal to 2. So let's look at the ellipse and see where these values point to. So we see that, we'll go to the next page. So we see that when lambda is equal to 2, when and y is equal to 1, x is equal to 2. So the coordinates would be 2, 1. And here it would be minus 2 and minus 1. And the coordinates here would be minus 2, 1. And this would be 2, minus 1. So we see, if we look at the ellipse here, this is the ellipse that with the constraint of x squared plus x squared over 8 plus y squared over 2, that's the ellipse. And we see when lambda is equal to 1, x is positive and y is positive. So that would be a point there. And when y is negative, lambda is positive, we also have this point where x is equal to minus 2 and y is equal to 1. It's more like this point and this point. Let me get rid of these things. Okay, so it is when minus 1 and minus 2, that's more like a point like this. I would say that point is minus, sorry, where is my eraser? So minus 2, x minus 2 minus 1 would be this point. X would be 2 and 1, that would be this point. So that is when lambda is positive. When lambda is negative, we see that it is in this quadrant. So positive 2 and negative 1, and here it's positive 2, negative 2, positive 1 in terms of y. So these are these two shown in pink is when lambda is equal to 2, and shown in green here is when lambda is equal to minus 2. Those are your critical points. Let's do one more question. So this question is taken from exercise 14.8, where fx is equal to, let me write that again, fx is equal, xy is equal to 49 minus x squared minus y squared. And here we see the constraint is x plus 3y is equal to, we call that gx, because we are omitting the constant term and we're going to call that gx. So from Lagrange we know that partial derivative with respect to a partial derivative of f with respect to x at the critical point x0, y0, and if you get the gradient vector, which is partial derivative of f with respect to y at x0, y0 is equal to lambda times partial derivative of g with respect to x at x0, y0, and partial derivative of g with respect to y at x0, y0. So let's do partial derivative of f with respect to x. So that this is a constant, so that would be 0. So the partial derivative of f with respect to x would be minus 2x, while partial derivative of f with respect to x, with respect to y should be minus 2y. And if g is this, we'll use a different color for that. If g is this, partial derivative of g with respect to x is equal to 1. Partial derivative of g with respect to y is equal to 3. So let's substitute that. So we have the gradient vectors is equal to lambda gradient vectors. So this value with respect to x's are written in pink. This is this value. So we say minus 2x, and with respect to y is written, this value is here, is written in green, 2y with respect to x. Of course, we know that is a critical point, so let's, for now, we'll write it as at critical points as x0, y0, and then we go and look at the gx. With respect to x would be 1, with respect to y, written as green, would be 3. So now we have two equations here, and we have another equation. The third equation would be, this would be, let me get it in a different color. This would be equation number 1, equation number 2, and the third equation would be x plus 3y equals 10. So let's take these three equations and solve them. So the three equations are minus 2x0 equals lambda 1 and minus 2, we should make these at critical points as well, 2y0 equals 3, and we have the third equation, x0 plus 3y0 equals 10. So for simplicity, we will delete the x zeros, and remember that whatever we get as solutions they belong to the critical points x0, y0. So here we see that, so this should be lambda. So let's rewrite these equations. Equation 1 would be minus 2x0 equals lambda times 1. And equation 2 would be minus 2y0 equals lambda times 3, or 3 lambda times 3. And we have the third equation, which is x0 plus 3y0 is equal to 10. For simplicity, we will get rid of the zeros, x zeros, and we will remember that this is valid only for critical points, and if we get any solution, that would be the value of the critical point. So we see here that x is equal to, so we have x is equal to minus, let's say minus x is equal to, we divide both sides by 2, then we get 2, and this implies x is equal to minus lambda over 2. That's a lambda. And from this equation, we can say, we can divide both sides by 2, so we could get minus y equals lambda, 3 lambda over 2. So we see y is equal to minus 3 lambda over 2. So then, if we substitute this equation and this equation to equation number 3. So we put x value and y value to this, we get minus lambda over 2 plus 3 times minus 3 lambda, now we're substituting for y, over 2 equals 10. So we do have a lambda here. Now we'll substitute, simplify further, over 2 plus 3 times, oh, it should be minus, because 3 times 3 minus 3 is 9. Lambda over 2 is equal to 10. We multiply both sides by 2, then we get minus lambda minus 9 lambda is equal to 20. So 10 lambda is equal to 20, lambda is equal to 2. So if lambda is equal to 2 from equation 1, lambda is equal to 2, we have from equation 1 we have minus 2x equals lambda which is equal to 2. So this implies x is equal to minus 1. From the second equation we have minus 2y equals lambda times 3, and lambda is equal to 2 times 3. So it's 6 minus 2y. So y is equal to minus 3. So I think I made a mistake here. So lambda is equal to minus 2 because it's minus 10 is equal to 20. So lambda is equal to minus 2. We do minus 2 here and we use minus 2. So x is equal to 1. And lambda is equal to minus 2 and it's minus 6 here. So y is equal to 1. So it's 1 and 3 is the critical point.